Hi, it's nice to be with you. That looks really fascinating, didn't it? Holy moly. Let me get right into it because I want to keep to the schedule and we've got lots of other folks coming up. So I'm going to talk for about 25 minutes or so on something called answering objections to the argument for intelligent design. And that's on the slide there, if you can see it. Steve talked a little bit about what intelligent design is, but as you may know, not everybody so far has agreed with our argument, and so I'm going to address a couple objections of the more prominent objections to the idea. But before I start, since intelligent design is such a controversial topic, I want to make clear that in case you were thinking otherwise, I'm not talking officially for my university or for my colleagues. My mother disagrees with me. These are just my ideas here. Okay, so this conversation really got started in earnest 150 years ago when Charles Darwin published his book on the origin of species. And it was really a very good idea and impressed a lot of people at the time and subsequently. And Darwin, like Steve was talking about, said that, well, suppose that an animal were born with a slightly increased coat of fur and it was a cold winter, then that animal would have a better chance of surviving than others of its species which had shorter fur, might be more exposed to the elements. And if it survived and if it produced offspring, then its offspring might inherit the same characteristic. And if the characteristic kept giving an advantage, then over time it would spread throughout the whole population. And it was a very good idea, and it explains many things, and it may explain many things about biology and continues to do so. But Darwin knew that although his theory could explain some things, there would be things that it'd have trouble with. And in The Origin of Species, he was talking about something called organs of extreme perfection in one section, talking about the eyeball. And at the end of his discussion of those really, really complex organs, he said the following. He wrote, "If it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous, successive, slight modifications, my theory would absolutely break down," adding, "but I can find out no such case." In this passage, Darwin was emphasizing that his theory had to be a gradual one. That is, evolution had to proceed in tiny steps over long periods of time with very incremental improvements. He knew that if animals suddenly improved in great leaps with brand new features all at once, then it would look suspiciously as if something other than random processes were involved. And so he always insisted on this idea of gradualism, very, very tiny and very slow, numerous steps. Well, okay, let's take Darwin at his word and ask, well, what sort of an organ or system could not have been formed, or surely does not look like it could be formed by numerous successive slight modifications? And one such type of system is one which I call irreducibly complex, or has the property of irreducible complexity. Now, irreducible complexity is a fancy phrase, but it has a very, very simple meaning. It just means you've got some system or a machine or something which has a number of different components, and the components interact with each other to perform some function that the individual components themselves can't do. Well, that's a bunch of words. Oftentimes it's easier to grasp a concept if you see an illustration. And an illustration of what I mean by this term is shown on the next slide. And this is a mousetrap. I told you it wasn't hard to grasp. A mousetrap that you could get at a hardware store, anywhere. And it turns out mousetraps have a number of different parts. Here, I'm going to use my mouse to follow along. And it's got this wooden platform here to which everything's attached. And it's also got this tightly wound spring with extended ends to press against the wooden platform here, and another extended end hooking over this other metal part called the hammer. And you've got to push the hammer over, and it's got to be stabilized in position, and that's the job of something called the holding bar. And the end of the holding bar itself has to be stabilized by being inserted into something called the catch. Now, the mousetrap needs all these parts to work. If it were missing the spring, or the hammer, or the platform, or any of the other parts, you would not have a trap that worked half as well as it used to, or a quarter as well as it used to. You would have a broken mousetrap. It would not work at all, like this microphone clipping over my ear. So this is what I mean by the term irreducible complexity. So it turns out that things like this are a big headache for Darwin's theory. Because if you wanted to evolve something like a mousetrap by something like a Darwinian process, numerous successive slight modifications, how would you do it? What would you start with? Would you start with, say, the wooden platform and hope to catch mice inefficiently? No, maybe you'd trip them or something like that. And then maybe you could add another part, maybe the holding bar. And then when they trip, they might impale themselves on the holding bar. No, that would be silly, because with irreducibly complex systems, the function only appears when pretty much the whole system's put together. So in the meantime, natural selection can't select for the function of the system. And so it couldn't be produced easily in that gradual fashion that Darwin envisioned. Well, mousetraps are very interesting. I think about them a lot. But what we really want to know is, are there any irreducibly complex biological systems? Or, since, as Steve mentioned, in the past 50 years especially, science has discovered that where the rubber meets the road in biology is at the cellular and at the molecular level. Are there any irreducibly complex cellular or biochemical molecular systems? And the answer is, yeah, they're all over the place. You can't turn a page of a biochemistry textbook without running into such systems. For example, here's the flagellum that Steve talked about. This is a drawing of the flagellum from a biochemistry textbook by Voet and Voet, which is used widely in universities across the United States. And as he said, this is quite literally an outboard motor that bacteria use to swim. This is the part here which acts as the rotor. It's spun around and around and around in a rotary fashion and pushes against the water and therefore pushes the bacterium forward. It's attached to the drive shaft by something called the hook region, which acts as a universal joint, allowing the rotary motion of the drive shaft to be transmitted to the propeller. The drive shaft is attached to a motor which uses a flow of acid from the outside of the cell to the inside of the cell to power the turning of it, just like water flowing over a dam powers the turning of a turbine. The drive shaft has to poke up through the bacterial membrane, and so some parts act as bushing material to allow that to occur without leakage. And I know this looks complicated, but let me assure you, this is just a little cartoon view of the bacterial flagellum. This is much more complicated than this illustration appears. For example, just as an example, the parts of the flagellum are not these nice little symmetrical geometric lozenge shapes and discs and so on. These are actually constituted of very complicated molecular entities themselves, proteins, which have to self-assemble and build this rather complex structure from the inside out. Nonetheless, I think this gives you the this is sufficient to get across the idea that, like a mousetrap, the flagellum is irreducibly complex. If it weren't for the hook, or the drive shaft, or the motor, or the propeller, you would not have a flagellum that spun half as fast as it used to, or quarter as fast as it used to. You would have a broken flagellum. Or much more likely, you would have no flagellum, because the cell, it turns out, has sensitive feedback mechanisms to tell it when the construction of this machine is going well or not well, and it will shut off construction if it senses that it's not going well in order to save energy. Now, I like to show folks this illustration of the flagellum because most people, when they look at this, quickly realize that this is a machine. This is not like a machine. It is not analogous to a machine. This is a real machine. And thinking about this might let us kind of figure out how we could explain where it came from. Now, let's see, where am I? Okay. Now, as Steve said, the science in the past 50 years has discovered, much to our surprise, that the cell is based on machinery. It's like if anybody's watched Star Trek and knows about the Borg, who are these kind of half-human, half-machine-like entities. They run on nanotechnology. Well, it turns out we do too. In that sense, we are the Borg. We run on nanomachines. For example, here's an issue of the science journal Cell, a special issue on molecular machines. And if you turn the page and you look at the table of contents of this journal, you find papers with titles such as "The Cell as a Collection of Protein Machines," "Polymerases and the Replosome, Machines Within Machines," "Mechanical Devices of the Spliceosome," "Motors, Clocks, Springs, and Things." So all of life, we now know, is based on these horrendously complex, elegant, sophisticated machines. Now, I wrote a book a while back, as Steve mentioned, arguing that Darwin's theory could not account for this machinery in the cell. It turns out that's not all that controversial. There are a number of scientists, besides myself, who agree that Darwin's theory is not up to explaining such discoveries. People like Stuart Kaufman of the University of Calgary and Lynn Margulis at the University of Massachusetts and so on. And they have their own ideas about what might replace Darwin's theory here. But my difference with them is that I've written that the best explanation for these things is that they were designed, purposely designed by an intelligent agent. And a lot of my critics have said, and I guess I should tell you that I do have some critics. Some of my critics have said, well, that Behe fellow, he's a known Christian. He has been seen entering and leaving churches. And therefore, this idea of intelligent design is a religious idea. It is not a scientific one. And that I'm letting my religious convictions interfere with my scientific work. Well, I appreciate their concern, but I disagree with them. I think the conclusion of intelligent design is completely empirical. And by that I mean that it's based entirely on the physical evidence plus standard reasoning that we use in everyday life. And as an illustration, let me show you the next slide here. This is a Far Side cartoon, if you guys know about it. And here we've got a troop of jungle explorers here, and the lead explorer has been strung up and skewered. And this fellow here turns to this guy here and says, "That's why I never walk in front." Words to live by, let me assure you. Now, everybody here looks at this cartoon, and you immediately realize that this was designed. This was not an accident. His death was intended. Now, how do you know that? Is it a religious conclusion? Oh, probably not. Probably not. No, you know it's designed because you see a number of parts interacting with each other to perform a function. Something like what I mean by irreducible complexity. And it turns out that we perceive design by something called the purposeful arrangement of parts. Whenever we see parts arranged to fulfill some function beyond themselves, we infer design. And that's what we have in spades in biology and molecular machinery these days. Well, okay, that's kind of the Cook's tour of the idea of intelligent design and irreducible complexity. Let's ask ourselves, well, what have other scientists said about these ideas? My book in which I spell these things out has been pretty widely reviewed by evolutionary biologists and molecular biologists and other scientists. What have they had to say? Well, they've had a lot of things to say, not all of them kind. Nonetheless, the most common response by most scientists is best summarized by a man named Franklin Harold, who's an emeritus professor of biochemistry from Colorado State. And he published a book a number of years ago, 2001 I think, called The Way of the Cell. And in it, he touched on the idea of intelligent design. And he said the following. He said, "We should reject, as a matter of principle, the substitution of intelligent design for the dialogue of chance and necessity." And he cites my book. "But we must concede that there are presently no detailed Darwinian accounts of the evolution of any biochemical system, only a variety of wishful speculations." Well, that's interesting. Let's pause here for a second. Dr. Harold makes 2 points, and let's look at them in reverse order here. He says that there are no detailed Darwinian accounts, no real Darwinian accounts of the evolution of any biochemical system, only a variety of wishful speculations, more colloquially known as just so stories, like the stories written by Rudyard Kipling over 100 years ago, how the tiger got its stripes, how the rhinoceros got its horn, how the bacterium got its flagellum. Well, it's funny, but if you think about it a little longer, it's really astounding that a theory that has the respect of the majority of the scientific community has been so utterly fruitless in explaining the basis of life, and it makes you think that some other theory might be called for. Okay, the second point that Franklin Harold makes is that he says we should reject, as a matter of principle, intelligent design. What principle? What principle is that? If you look at something like the flagellum, that drawing of the flagellum I had up, intelligent design is not something that's hard to see. It pops into your mind right away, but apparently we are forbidden from entertaining the idea of design based on some particular principle. What is it? Well, it turns out he doesn't say. He just writes those lines that I showed you, and then he goes on to other topics in his book. Nonetheless, I think I have a good idea of what he intended by that, and it's shown here on the next slide. If we could have that up for the entrance here. And that is this, that that intelligent design seems to point strongly beyond nature. It seems to have philosophical, maybe even theological implications, and that kind of makes a lot of people nervous. And a lot of people think that science should stay away from theories that have such strong extra-scientific implications. Well, again, I understand that sentiment, but I disagree with it. When I was being trained in graduate school and so on, we were always told that science is supposed to follow the evidence wherever it leads. Let other people worry about philosophical or other implications. And I thought that was a good idea then, and I continue to think so. Okay, now I'm going to turn from a kind of a basic explanation of design to specific objections. And I'm going to look at, if I have time, a legal objection, and then a conceptual objection, and finally a scientific objection, if we can get to all of them. But the